Ladies and gentlemen, my name is Shreya Sharma, and I'm a part of Dr. Peter Tong's Big Data Analytics class of 2023. My project is about big data analytics in diamonds, specifically creating and evaluating predictive models. Accurately predicting diamond prices is of critical importance to the precious metals industry. It allows stakeholders such as diamond dealers, buyers, and investors to make informed decisions based on reliable estimates. By leveraging the power of big data analytics, we aim to create a robust predictive model that can accurately estimate the retail value of solitaire diamonds. By achieving this objective, we aim to contribute to the understanding of the diamond pricing factors and facilitate decision-making processes within the industry. So what are some of the tools that we use to complete our analysis? So to set up a development environment, we use Jupyter Notebook, Anaconda, as well as Python to interface with Python libraries. The Python libraries we use for data visualization include matplotlib and Seaborn. For data processing, we use pandas, and for machine learning, we use scikit-learn. In order to create our own cross-validation dataset, we use Microsoft Excel. So what is the methodology behind this project? The process is pretty straightforward. We're first going to go ahead and obtain data. Then we're going to do some data pre-processing. We're going to then train our 4 models on this data. We're going to evaluate the model performance, and then we're going to do cross-validation from an external data source. So let's go ahead and familiarize ourselves with the dataset behind this project. Our dataset consists of over 60,000 GIA-certified diamonds. That's over 600,000 data points within our training dataset. As for our cross-validation dataset, what we've done is we've created a specialized dataset from Blue-Nile, a GIA-certified dealer of solitaire diamonds, and we're going to go ahead and take our models and compare their accuracy on real-world data. So within our training dataset, we have carat, which is the weight of the diamond. We have cut, which is a ranking of how well the diamond has been cut. The color, how clear the diamond is. Clarity, how transparent the diamond is. Depth and table, which both relate to the brilliance of the diamond. Then, of course, we have our dependent variable, the price, what we aim to be predicting. And then we have our dimensions of the diamond in X, Y, and Z axes. Let's go ahead and dive into the first part of our project, data wrangling. Looking at the data set, you can immediately tell that we have a lot of string data types. The cut, the clarity, and the color, 3 of our 4 C's, need to be processed before we can directly pass it off to our machine learning algorithms. So these are all in string data type, and machine learning algorithms cannot directly process this. So for our machine learning algorithms to process this, we need to convert this into some sort of numeric data type. And to quickly convert over 200,000 data points, we chose to employ one-hot encoding, a specialized machine learning technique that works on converting string data type into something a machine learning algorithm can directly process. So what exactly is one-hot encoding? Well, one-hot encoding is a process of transforming categorical variables into binary representation. So each unique category becomes a separate feature column, where the presence of a category is indicated by a value of 1, true, and absence by 0, false. Essentially, we convert our string data type into a Boolean data type using numerical values of 1 and 0. So let's take a look at the example we have on screen. We have a standard data type, which is quite similar to the one that we had in our own, which is the color, right? That's the feature. Now within color, you have red, green, yellow, green, and red again. What one-hot encoding does is it converts this into a vector, which you can see in the one-hot encoded vector table. And then what it does is it creates 3 new columns, red, green, and yellow, all the colors that were originally within all the rows actually, that were originally within the color column. And essentially, it splits up the data into something that's much smaller and can be directly processed by our machine learning algorithm. It enables the inclusion of categorical data in machine learning algorithms that only operate traditionally on numerical values. Next, we're going to go over the 4 models that we've selected to train on this dataset and evaluate their performance. So first, we have our standard linear regressor, followed by gradient boosting. After that, we have a neural network, and we end on a random forest algorithm. So let's get into our linear regressor. A linear regressor is a popular machine learning algorithm used for predicting continuous numerical values. What this algorithm does is that it assumes a linear relationship between input features, the independent variables, and the targeted output variable, which in our case is price, the dependent variable. The algorithm aims to find the line of best fit within this data, and it does that by minimizing the difference between the predicted values and the actual values of the training data itself. The line can be directly represented by a simple equation of the form y is equal to mx plus b, where y is the target variable, x is the input feature, and m is the slope. B is just the y-intercept. The algorithm calculates the optimal value for m and b using statistical techniques such as least ordinary square or gradient descent. During training, the algorithm adjusts the values of m and b iteratively, meaning that it can go back and change them to minimize the error between the predicted and actual values. Thus, the linear regressor is one of the simpler algorithms that we can use that essentially assumes a linear relation between our independent variables and our dependent variable. The accuracy that we received on our linear regressor was roughly 91.8% for R-square value on the training and cross-validation data set. Following that, we have our gradient boosting machine learning algorithm. So this, similar to linear regressor, is a very powerful machine learning algorithm that combines multiple weak predictive models, which in our case are decision trees, to create one strong predictive model. The algorithm works in an iterative way, just like the linear regressor, and it builds a model using a stage-wise fashion by minimizing the loss function. In each stage, a new weak decision tree is added to the ensemble by fitting it to the residual, which is just the difference between the predicted and the actual values of the previous decision tree. The new model is trained to find the best split points of the data based on the gradient of the loss function, hence the name gradient boosting. The R-square value for the gradient boosting was significantly higher than that of the linear regressor at 95.4%. Okay, so up third, we have our neural network. A neural network is a machine learning model that's inspired by the structure of the human brain. It consists of interconnected layers of artificial neurons called nodes or units. Each node takes an input, it applies a complex mathematical function to it, and it returns an output. The network learns by adjusting the weights and biases associated with each node to minimize the error between predicted and actual values. This learning process is called training, and it's typically done using algorithms like backpropagation and gradient descent. The algorithm can have multiple layers, as we can see in the diagram: the input layer, where we put in our independent variables, the hidden layer, where all the complex calculations are done, and the output layer, where our dependent variable, price, is returned. Deep neural networks with many hidden layers are capable of learning intricate patterns and representations. Once trained, they can make predictions on new and unseen data. Neural networks have achieved remarkable success in various fields, including image and speech recognition, natural language processing, the principle that ChatGPT is based on, and even autonomous driving. So it definitely makes sense to apply such a powerful algorithm to our own project to see how we can apply this. The problem with neural networks is that they traditionally require careful tuning and large amounts of training data, and they're easily, out of all the algorithms we've mentioned so far, the most computational power heavy. As for our neural network, which took quite long to run on Jupyter Notebook, we returned an R-square value of roughly 95%, which is quite high. And then last but not least, we have the random forest algorithm. Now, the random forest is an assemble method that is similar to gradient boosting in some sense. A random forest is essentially a forest of decision trees that combine their prediction to essentially create a forecast. Now, each tree is trained on a random subset of data, making it incredibly diverse and less prone to overfitting. Each tree learns to predict the target variable based on different combinations of features that are completely random. And the final prediction is obtained by averaging the prediction of all the data trees. After that, the random forest model goes ahead, it does majority voting, and averages out all of the predictions by the trees, and we get our final result. Random forest models are incredibly robust and less prone to overfitting as compared to individual decision trees, which can develop very strong biases. For us, the random forest returned the highest R-square value at 97.49%. Let's move forward to our conclusion. So why was the random forest the most accurate out of our 4 machine learning algorithms? Well, to put it straightforward, the random forest algorithm's ability to handle highly dimensional categorical data, like the features in our diamond dataset, contributed to its superior performance. The neural network requires a large amount of training data to effectively make predictions. Perhaps our training dataset was not big enough for a fully operational neural network to predict such complex tasks. As for the linear regressor, the regressor assumes a linear relation between the independent and the dependent variable. The problem is, with diamonds, it is not nuanced enough to capture the characteristics of diamonds. Yes, diamond prices do definitely increase as, let's say, the clarity of the diamond increases, but another thing is it does not increase in a linear way. It increases in more so an exponential or logarithmic way. This is because the more clear a diamond is, the more valuable it gets. And not only that, but at that point, the diamond becomes more and more rare, which immediately increases the price people are willing to pay for the diamond. So that's an area where the linear regressor went wrong. As for gradient boosting, the algorithm's strength lies in its ability to learn from the gradients of the loss function, which may not have been as effective with the categorical features of our dataset. So before we wrap up, a couple weeks ago, Dr. Tong was telling me that given my big data presentation is about diamonds, it should only be right that I bring in a small token of appreciation for you guys, the audience, to thank you all for listening to my presentation. Now, I'm very, very proud to say I've actually done just that today. If you all look under your seats, you will find a small 3-centimeter piece of coal, just like this one. While I have not been able to purchase diamonds for you all today, essentially what I've done is I've made a $1 million investment for each and every one of you. I promise that if you hold on to this piece of coal for maybe 10 billion years, you're going to be holding what could potentially be a $1 million diamond in your hand. To quote Henry Kissinger, the former Secretary of the United States, "A diamond is a chunk of coal that did well under pressure." Ladies and gentlemen, big data analytics in diamonds, creating and evaluating predictive models. If you'd be interested in taking a look at some of the source code that's gone into this project, be sure to check out the QR code up above. It has been an absolute pleasure to present to you all, and thank you so much for watching.